In this video, we talk about classical linear factor models. We talk about how the I-CAPM, Fama-French three-factor model, and Mertons Intertemporal I-CAPM relate to the concept of linear beta pricing models. We also talk about how to incorporate factors that are not tradable. So we start with the I-CAPM. The I-CAPM is a special linear factor model. It assumes the following. As F is tradable, its market price of risk coincides with the following expression. The Fama-French three-factor model is a special linear multi-factor model. It assumes the following. Notice, RHML is an excess return from a strategy that goes long value firms and shorts growth firms. Similarly, R size is an excess return that goes long small market cap firms and shorts large market cap firms. All three excess returns are tradable, so the respective elements of the market price of risk vector are as follows. Now the intertemporal I-CAPM of Merton, also called the I-CAPM, is an especially elegant linear factor model. In a 1973 publication of Professor Merton, a Markowitz investor is confronted with a time-varying investment opportunity set. The level and slope of the capital allocation line are stochastic in that framework and move across time. Merton derives in that paper that the optimal asset allocation is made up of three portfolios: the money market account, the classical tangency portfolio, and something which is called a hedge portfolio. The hedge portfolio is chosen such that it pays out well in times when investment opportunities deteriorate. Merton derived that risk-averse investors want to hedge that risk. Essentially, this means they want to hedge the risk that the level or slope of the capital allocation line reduces. Any factor that moves either the level or the slope of the allocation line is considered to be a systematic risk factor that comes along with a non-zero factor premium. The respective linear factor model for expected returns and systematic risk equals, according to the I-CAPM, that expression here, where lambda m is the I-CAPM style market risk premium, beta im is the I-CAPM style beta factor of asset I with regard to the market, and now new lambda l, for L being 1 to k, is the price of risk for innovations in risk factors L. And the beta IL is the normalized amount of co-movement of asset I's return with innovations in risk factor L. Remember, any factor that affects the evolution of the level or slope of the capital allocation line is part of the set L, which consists of these 1 to capital K factors. So, one of my favorite applications of that I-CAPM setting is the 2006 JF paper of Professor Petkova. Now, Petkova shows that a linear multi-factor model that extends the I-CAPM by innovations to the dividend yield, innovations to the term spread, innovations to the default spread, and innovations to the 1-month treasury yield captures the US cross-section of expected equity returns better than the Fama-French three-factor model. And that has been interesting for three reasons. First, the rationale for Petkova's analysis is the I-CAPM of Merton, hence it's an equilibrium framework. Second, the risk factors that extend the I-CAPM are fundamental shocks, allowing to connect these to the state of the business cycle. Third, in order to interpret the risk factors, Petkova applies a Gram-Schmidt orthogonalization onto the risk premium factors. See a previous video on that. Now, Petkova also found that the value premium seems to be a duration risk premium, whereas the size premium seems to be compensation for distress risk. Methodology-wise, Petkova uses a linear vector autoregressive system for the market excess return, the dividend yield, the term spread, the default spread, and short-term interest rates to, and now importantly, back out the innovations, which means the epsilons, for these respective time series. Now next, she regresses each US stocks excess return onto the innovation terms that she just backed out in order to find the factor risks beta. Last, she determines the market price of risk lambda by using the two-stage least squares approach of Fama-Macbeth. Now don't worry, I'm going to post additional videos on how to estimate vector autoregressive systems and on the just mentioned Fama-Macbeth procedure. So I want to close that video here with a question, with the last question for now. How to incorporate non-tradable risk factors like GDP growth, unemployment, inflation, debt, whatever. Now, I want to talk about two approaches. The first approach is to follow the I-CAPM notion, similar to the just mentioned 2006 JF publication of Professor Petkova. Doing so is expected to work well if the non-tradable risk factor that you consider is a factor that indeed drives the level or the slope of the capital allocation line. Now, for all other cases, you are left with finding a tradable factor mimicking portfolio. So that would be the second approach, and use that if the I-CAPM storyline doesn't work. So practically speaking, for a factor mimicking portfolio, you will run a linear regression of your non-tradable risk factor on a bunch of tradable asset returns. The resulting projection coincides with a tradable portfolio. And that portfolio has maximum correlation with the non-tradable risk factor. So let's go through some basic math to see exactly how that intuition translates into equations. If you're fine with the intuition, you can just stop the video here. Otherwise, let's go through these equations together. Assume that risk factor Fj is not tradable, while all the other FL factors, for L being different from J, are tradable risk factors. So our objective is to substitute the non-tradable Fj with its factor mimicking portfolio. Hence we regress Fj onto a vector of tradable returns, which we call R star. The projection looks as follows. Now let's define the projection of Fj on R star as X. So X is nothing else than the gamma plus beta R star. And keep in mind, the gamma and beta are determined by the regression from the previous equation. Now, in other words, X is the return on a tradable portfolio that best mimics the non-tradable risk factor Fj. So in order to get risk exposure of an asset I to the non-tradable risk factor Fj, we approximate the covariance of Ri with Fj exactly with the covariance of Ri and X, the mimicking portfolio. So therefore the covariance of Ri with X will be beta times the covariance of Ri with R star. Now, in order to get the market price of risk for the non-tradable factor fj, we compute the following. The resulting linear multi-factor beta pricing model equals the following expression, where for all L not equal to J, lambda L1, so that's the market price for L, coincides with the expectation of FL if FL is a tradable excess return, or lambda L equals the expectation of FL minus RF if FL is a tradable return. If you look at both approaches carefully, you will notice that the key difference is in the calculation of the market price of the non-tradable factor. The I-CAPM approach uses the Fama-Macbeth procedure to determine the market price of non-tradable risk, while the factor mimicking portfolio relies on the expected return of a linear factor mimicking portfolio. Another noteworthy difference is that the I-CAPM approach is grounded in economic theory. In contrast, the portfolio mimicking approach exploits correlations.
Got feedback? We would love to hear it. Please drop us a line. And if you liked the video, give it a thumbs up. And don't forget to subscribe to the channel.